an example here. Part of an example from Vardaman and Job from the text. So this is from page 21 of Statistical Quality Assurance Methods for Engineers by Vardaman and Job. What you'll find there are some measurement data. I'm going to look at a very small part of the data set that's on page 21. There were 3 students involved in a measurement study. I'm just going to worry about student 2 and student 3. And they made some measurements on the heights of some punches. And I'm only going to consider punch 1 and punch 2. And student 2 on punch 1 measured a 497, a 499, and a 497. Student 3 on that same punch measured a 497, a 498, and a 496, and student 3 on punch 2 measured a 497, a 499, and a 500. And for the units here are 10 to the minus third inches. And so these punches were about half an inch tall. Notice that this is a problem where if I look at the structure of what I've got here, these represent 2 different measurands. Those are different. Those provide me different x's. And the measurement study was one where both students used the same piece of equipment and the same measurement protocol, but there were 2 different individuals involved. And so this is a case where you might think of this as being device number 2, say, and this being device number 3, or device 1, device 2, however you want to name things. Okay, so what might I learn from data like this? Well, if I think about the structure here, I might first consider comparing the 2 students, comparing the results for student 2 to student 3. I could represent what I'm going to do then in terms of another picture. So let's insert this picture. I could think about this problem as one where this thing is represented by this is punch 1 true height, and device number 1 over here, say, is student number 2, and device the second device is, say, student number 3. Again, device meaning combination of person, equipment, and protocol. And what I want to do is compare student 2 to student 3. And if I look down here at what I have for means and standard deviations for these two samples, I see that the mean, that one mean is the measure n plus one bias, the other mean is the measure n plus the other bias. So this is a situation where the difference in the two means is the difference between measure n plus the first bias and measure n plus the second bias. Since I have the same measure n, it's just the difference in the two biases. So my point is that my t-interval for mu1 minus mu2 gives an inference for the difference in the two biases. And if I compare standard deviations, well, that means I need to look at what's written down here and say, well, the first sample has variability that is described by the variability of the first device. The second sample has variability that's described by standard deviation for device 2, and so this is a ratio of device standard deviations. And so let me just then apply these basic two-sample confidence intervals to this problem and see what we come up with. For comparing, say, let's make 95% limits for, say, difference in biases, and for sake of argument, let's take, say, student 3 minus student 2. What I'm going to do is take the difference in y bars, which is 497.0 minus 497.6, and I'm going to hedge that by a t-value times the square root of 1 squared over 3 plus 1.155 squared over 3. And it looks like I pulled a rabbit out of a hat here. Where did these numbers come from? Let me go back in this series of slides. And let me tell you that some summary statistics here are that this has a y bar of 497.6 and a sample standard deviation of 1.155. This set of numbers has a average of 497.0 with a sample standard deviation of 1.00, and as long as I'm at it, let me tell you that these numbers have a sample standard deviation of 498.6 with a sample standard deviation of 1. This thing's getting sloppy, isn't it? Sorry about that. 1.5275. And so I'm making use then of these values and these values to make a comparison between student 2 and student 3 biases by looking at a single measurand and making confidence limits for a difference in averages. So that's the origin of the 497.0, the 497.6, the 1 squared, and the 1.155 squared. The only mystery here is what to use for a t-value. If we're going to make 95% limits, we want an upper 2.5% point. What about degrees of freedom? Well, if you plug and chug with that strange looking Satterthwaite formula, what you want is 1 squared over the sample size of 3 plus 1.155 squared over the sample size of 3, that squared over 1 to the 4th over sample size minus 1, which is 2, times the square of the sample size, that's 3 squared, plus 1.155 to the 4th over sample size minus 1, which is 2, times 3 squared, and ... If you do the arithmetic, that turns out to be 3.92. An alternative is to take the smaller of the 2 degrees of freedom that you would have from either of the 2 samples, that is the smaller of 3 minus 1 and 3 minus 1. So this is something that's bigger than 2. It is not as big as 3 minus 1 plus 3 minus 1, which is what you would use if you assumed that the 2 populations had the same sigma and used the pooled standard deviation instead of these 2 sample standard deviations in this formula. You check it out. If we take this 3.92 and round down to 3, the upper 2.5% point of the t-distribution with 3 degrees of freedom is, I believe, 3.182. And so when all is said and done here, what one has is minus 0.6 plus or minus 2.81. And basically what that tells me is that I see a difference in the averages of student 2 and student 3, but these sample sizes are so small that I can't really tell whether student 3 is biased higher or lower than student 2. That is, this number is known with this kind of uncertainty, and that kind of uncertainty is bigger than the difference, and so I can't really say definitively which student tends to give bigger answers. So there is no conclusive evidence of a difference in biases.